One of the ways we often characterize the speed of a reaction is to talk about its half-life, and that's going to be the topic of this video. So our learning goals are how to define the half-life of a reaction and do this for different rate orders and see how they compare. So what is a half-life? Half-life is basically the time it takes to use up 1/2 of the starting material. That is, we start with some amount of reactant. When does it reach half of that amount? So from the first order integrated rate law, what we might do is say, how long does it take for that initial amount, A0, to be reduced to 1/2 A0? So the way it would look mathematically is something like this. What I've drawn here is the concentration of A at time T1/2, which I'm going to define to be the half-life. And that has to be equal to 1/2 of the initial amount, 1/2 of A0. Now, if it's a first order integrated rate law, we know that at a later time T1/2, that concentration must be equal to the initial concentration times e to the minus k times t to the 1/2. So I can now set these things equal to each other and have 1/2 A0 is equal to A0 times e to the minus k T1/2. And notice that I have A0 on both sides of the equation, and it's there in the same factor. So I can divide both sides by that and then solve for the value of T1/2. When I do that, and I'm not going to go through all of the math here, but we get a relatively simple expression for that. T1/2 is equal to natural log of 2 divided by the rate constant K, and natural log of 2 is 0.693, and there's a few more decimal places as well. So in the end, we get a very compact expression for the half-life of a first order reaction. Now a key here is that the half-life does not depend at all on the initial concentration. So in other words, no matter how much stuff I start with, if it decays or if it reacts by a first order rate process, the half-life is not going to depend at all on how much I started with. So some observations about this. If I have a small value for the rate constant, that's going to be in the denominator, so it means T1/2 is going to be large. Well, T1/2 is a measure of how long it takes for this system to react. So that's telling us that if it's got a large half-life, the decay is slower. So small k corresponds to a slower reaction. A large k, on the other hand, would be a shorter half-life. K in the denominator, if it's larger, it's going to be a smaller T1/2. So we can see right here a direct correlation between the value of K and the speed of the reaction. And the speed of the reaction is going to be directly related to the size of K. Now the half-life, as I mentioned, depends only on K and not on A0. So for a first order rate process, this is what it might look like. I've drawn a picture. The graph, the curve that's shown there, is the integrated rate law for a first order equation. And let me explain what else I'm showing there. I'm showing you the formula for T1/2. Now, if I start at A0 up on the vertical axis, if I go down 1/2 way, that would be to 1/2 A0. Now, if I draw a line across from that, horizontal line, to the curve, that point will be at the time T1/2. So I can drop a vertical down from that, and it basically creates that rectangle that's blue colored on this graph. So the blue rectangle is what tells me about the first half-life. Now, if I go down another half from there to 1/4 of the initial concentration and draw a line over to the curve and then draw a line down, that takes me to the second half-life. Now, in this case, it's exactly equal to double the first half-life. If I do it a third time down to 1/8 A0, that would take me out to 3 T1/2, and to the fourth one it'd take me out to 4 times T1/2. But the key here is that in a first order reaction, all of the half-lives, all of the successive ones, are the same length. So in other words, the distance between T1/2 and 0 is equal to the distance between the second half-life and T1/2. And it's also equal to the distance between the third half-life and the second half-life. This is true only of first order reactions, but it's an interesting and I think a beautiful mathematical symmetry that comes about in those reactions. Let's see what happens for other orders. So if we look at zero order reactions, you may recall that in a zero order reaction, the rate is just equal to the rate constant. All right, so the change in concentration, that is when we run for some small period of time, delta t, the change in concentration would just be that rate constant times delta t. Since the reactant is disappearing, it's got to be negative k delta t. So that means when we work out the time evolution, in other words, when we figure out the integrated rate law for a zero-order equation, it'll be a at time t minus a at time 0, equals a at time 0 minus kt. And so this is the characteristic curve that one would get for the integrated rate law of a zeroth-order rate process. You notice that it's just a straight line. Well, that's because the rate is constant and it's a negative. It's going to be a negatively sloped line as drawn here. Now, if we take the same analysis that we used for the first order, so I'm going to go down from my initial concentration, A0, down to 1/2 A0, and then draw a horizontal line across to the curve. That tells me where the first half-life will occur. But notice something interesting happens this time. When I go to the next half-life, so I go down to 1/4 A0 and draw a line across, that one's going to drop down on the second half-life, but the distance between that time and the time of the first half-life is somewhat shorter than the length of the first half-life. If I do it a third time, that distance will be shorter still. Now, we could we could see that this will continue on, but the net result for a zeroth order reaction is that the successive half-lives all get shorter. And they all get shorter because they're now starting at a point that is half of the concentration of the previous half-life, and because the half-life itself is directly proportional to where it starts, and that's what the equation in red is showing us there. Because it's directly proportional to the place where it starts, as that starting point gets smaller and smaller, the half-life itself gets smaller and smaller. So what happens for second-order reactions? Well, recall that for a second-order reaction, the rate is equal to k times the concentration A squared. Now, I won't go through the math for deriving this, but the integrated rate law would look like this, where we have 1 over the concentration at a time t is equal to 1 over the initial concentration plus kt. Now, what does that look like? Well, interestingly, it looks a lot like a first-order reaction. It's a decaying curve that ultimately decays to 0, starting at the value of A0 at time 0. Now, how does that affect the half-life? Well, if I draw out my curve again and draw the half-lives on it, I've drawn an expression for the half-life, a written expression for the half-life there in red. But what I can see is that with each successive half-life, figured out in the same way that we did for the first order and the zeroth order, the successive half-lives are getting longer. All right, now again, we can analyze the expression for T1/2 and say that since it's inversely proportional to the starting point of that particular half-life, as the starting point gets smaller, the T1/2 should get larger. So we have an interesting, I guess, a way to summarize this is an interesting correlation between zeroth, first, and second order rate processes. For the zeroth order process, successive half-lives get shorter. For a first order rate process, they stay the same length throughout. And for a second order process, they get longer.